Uh, yeah. Can you see my screen and am I audible? Is my screen visible? Oh, okay. Okay, then I'll begin. Yeah, this is it. Okay. Welcome everyone. We are in the problem solving session 4 for the biochemistry NPTEL course. And if you remember last time, we had done enzymes and we solved a lot of numericals. So today also we have enzymes. Today we have a new topic on enzyme kinetics, and then the second half of today's lecture, as you would see from your lecture notes, this was about so polysaccharides, monosaccharides, so carbohydrates and lipids. So lipid I haven't covered in today's session. We can do that in the next week because we have more topics on lipids for the week 5. So today we'll do enzyme kinetics remaining portion, and then we will do carbohydrates, which is something that we have already done in the first introductory class, but we'll do it once again in a proper and more detailed way. So before we jump to new topics, let's just brush up the previous topics and do few numericals that were left in the previous class. So we did enzyme kinetics in the previous session, where we looked into how do we look into the kinetics of the formation of product from the substrate when there is an enzyme involved. So we looked into the Michaelis-Menten equation, and we looked into this kind of an equation where we see E plus S forming ES, which further gives rise to product. Just a second. Maybe not. Yeah. So and then we had the rate constant for each of these reactions in each direction. So E plus S forming ES is a forward direction. So this is shown by K1, while the process of breakdown of ES into E plus S is denoted by K minus 1. Similarly, formation of E plus or breaking of ES into E plus P, which is product and enzyme, is K2, while the opposite is K minus 2. And then we saw the equation, which was Michaelis-Menten equation, where we see that V naught is equal to V max into S Km plus S. We then looked into how to derive, how to come to this formula here. How did we get this Michaelis-Menten equation? We started with the rate of ES formation and rate of ES breakdown. And then we assumed, when we had the steady state assumption into action, where we believe that the concentration of ES, that is enzyme substrate complex, stays constant over time. Then we did all these equation and substitution, and we finally came down to it. From there, we found out what is Km. Km is equal to the substrate concentration at which the V naught, or the velocity, or the reaction is at its maximum, half of its maximum. So V max, one half of V max. So Km is S, where V naught is equal to half of V max. We also saw this. And then we use this equation in a straight line formula, straight line curve. Sorry. Yeah. Which is called Lineweaver-Burke plot, and we saw how to plot it. So we basically invert this equation, bring it to n y is equal to mx plus c form, and then we have the slope, we have the y-intercept, and we have the x-intercept, and we can see how do we calculate each of these values. And we did a lot of numericals. So a brush up on those numericals. We'll do numericals today also, maybe 2 or 3, so that you get the concept once again. And these are very easy questions, so you shouldn't take much time. So here's the first question. Your y-intercept on the plot is 4, and your x-intercept on the plot is -2. So what is the Km? So in one, remember, one intercept is 1 by Vmax, one intercept is -1 by Km. So you have both these intercept values, and you are asked what is the Km value. This is not a very difficult question, rather it is very easy. So let me know if when you are done with the answers in the chat box. One value is 4, one value is -2, and you're being asked what is the Km value. Point 0.5. 0.5, right? So if people are attempting, I will just show the solution and you can check if you were thinking in the correct direction. So this is how our LV plot looks like, right? You have 1 by Vmax as the y-intercept and 1 minus 1 by Km as your x-intercept. And you have these two values given to you, out of which you are simply asked what is Km. So you can simply do this, take this equation, minus 1 by Km is equal to -2, and then calculate for Km, which is basically minus 1 by -2, which is 0.5. Yes. Okay. So let's go ahead. Now this question. An enzyme catalyzes the conversion of 30 micromole of a substrate to product at a reaction velocity of 9 mu mole per second. When ET, which is total enzyme, is 30 nanomole and Km is 10 micromole, K catalytic efficiency, so K cat by Km of enzyme will be n into 10 to the power 7. So forget about the value here. You need to calculate K cat by Km. So you calculate, you already have Km value. So you need to come to K cat. K cat is, if you remember, when we are using Vmax equation. So you try attempting this and then we can discuss the answer. So you are given the value of substrate concentration, value of V, value of ET, and value of Km, and you need to find K cat by Km. Okay, someone says 30. I will wait for others also to try and attempt. Let me see if anyone has any doubt into this. So you are given V, you are given S, you are given Km. You need to find out what is the value of K catalytic efficiency, which is K cat by Km. Also, I would like you to point out one more thing. If you look into this question and the values given, they are in micromole unit, while the answer is required in moles. So micromoles and moles. So you need to convert that Also, the unit also need to be checked, taken care of. Yes, you can unmute or you can type your questions. I am on the screen, so I can look into the doubt. Or you can also unmute yourself and ask if you have any doubt. Dipali, do you have a question? Your hand is raised. Okay, someone else says 4. So, okay, let's look into the answer because it might take a while because there are many things happening in this question. So yeah, the answer is 4, and we'll see how. Like there are steps to it, so let's do it one by one. So of course we begin with the Michaelis-Menten equation, which is V is equal to V max X divided by Km plus S. Now from this we are given our velocity V 9 micromole per second, our S 30 micromole. We also have been given Km, which is 10 micromole, and we know ET. We'll use ET later. For now, for the time being, we can calculate V max because we have everything else. So if you substitute that, V is equal to 9, which is equal to V max into 30 and 10 plus 30. Now I can put all of them together because they are all in the same unit. They are all micromoles. So if I solve this, V max is equal to 12 micromole per second. Is the usage of this formula clear? This is pretty straightforward. Okay. So now from this equation and this solving, we got to know that Vmax is equal to 12 micromole per second. Now, we also know Vmax, which is the maximum velocity, is equal to K2 into ET, total enzyme. K2 can also be written as Kcat in case where K2 is the rate limiting step. So Kcat into ET, and generally in the catalytic reaction, K2 in one step catalytic reaction, K2 is a rate limiting step. So Kcat is equal to K2. So you can write Vmax is equal to Kcat into ET. Now here too, we already have calculated Vmax. We know Km, but that's of no use to us right now. We'll see how, and we know ET. So we need to find Kcat. So let's do that. We simply need to divide Vmax. We divide it by ET. So Vmax we know 12. ET we know is 30. Now one is in, if you see, one is in micromoles and one is in nanomoles. So need to convert one of them into nanomoles. Let's do it nanomoles first. So 12 into 1000 for it coming into nanomoles, and we have 400 seconds. Now that is your Kcat. The question is Kcat by Km. So Kcat by Km 400 by 10. And we need to convert this into moles. So I converted this into moles and I got 4 into 10 to the power 7 mole per second. So let me know in this slide if you have any doubt. Any doubt? Okay. Okay. So yeah. So you need to remember, this was straightforward, only that you need to remember how do you put Kcat, which is equal to K2. So now this question, again, usage of several instances. So an enzyme that follows Michaelis-Menten's kinetic catalyzes the conversion of 35 micromolar substrate into product with a reaction velocity 10 micromole per second. So you have velocity, you have substrate concentration. The Km and Kcat are also given to you, 14 micromole and 500 seconds per second. So the total amount of enzyme taken for the reaction is how many nanomole? Check for the units, and this is similar to the question we have done previously. Same equations. Just be careful of the units that we are considering here. Same equations, just be careful how you are converting one unit to another unit. Yeah, someone has written 28. Okay. I'll wait for others because we are few in number. So I'll wait for other answers and then we can discuss them. Dipali, do you have any questions? Because your hand is raised. If not, then I'll just remove it. Okay, I have another answer, 28. We have one person. I will wait for 1 minute if you want to answer, and then we can discuss. Okay. Uh, I will show the answers. Meanwhile, if someone is still attempting, they can check where they were and if they are going the correct direction. So as you people have written 28, which is correct answer. And as we've already said that it's basically the same equation that we used in the previous question. So B is equal to V max into S divided by K plus S. And we have these values given to us already in the same unit. So we shouldn't worry. We can directly substitute and we get the value of V max. Then we have Vmax, which is equal to Kcat into Et, where again we have Vmax in micromoles and we have Kcat. So we did that. Now Vmax we know, we have Kcat, we have Et. We did the calculation, but the answer should be in nanomoles. So we have multiplied it respectively and our answer is 28 nanomole. Is this clear? Yes. Sorry, what? Yes, 0.2028 micromole, which is 28 nanomole. Exactly that. Let me know if you have doubt. Otherwise, we can go to the next question. Okay, cool. So let's go to the next question. These are all still related to Michaelis-Menten's equations and kinetics. So let's do these first. So read the question properly and then we can answer it. So the rate constant for the enzyme E binding to its substrate S is 4 into 10 to the power 7 per second. The rate constant for the dissociation of the ES complex is 7 into 10 to the power per second. The rate constant for the formation of product is 9 into 10 to the power 5 per second. So you have three different rate constants given to you. You can place them accordingly in the equation that we know. Now, based on this information, you have these 5 options, which talks about dissociation constant and Michaelis-Menten's constant. So my suggestion, you try to solve both the values and then you come back and answer which of these is incorrect. solve it for dissociation constant, solve it for Michaelis constant, and then come back and check which are values or which of these options are incorrect. Take your time and solve it easily and clearly. A, B, C, D, E. You mean to say all of them are incorrect? Okay. I'll wait for others to answer and we can then check. Meanwhile, Dipali, right? Could you give me the values of dissociation constant and Km? Which value, what are the respective values for Km and Kd, dissociation constant? Okay. P. Okay. A, B, D, E are incorrect. Okay. A, B. Okay. So just to be clear, but could you people write your values for KD and KM in the text box so that I know that you people have done this correct calculation? So what is the value that KD that you have got and what is the value of KM that you have got? KM is 0.004, okay. And sorry, KD is KD is 0.0174, okay. Yes, 0.004. There's 0.004 and there's 0.04. Which one is value is correct? We'll see. Okay, so I think we have got answers here. Yes, please be careful of your points. Please be careful of what you are answering. And do you want to give me the incorrect options, Aditi, or shall I give the answers? Because it seems like you have already solved the values. So I have ABC, I have ABCDE, and I have ABDE. Maybe I'll give the answers and you can check. So B is incorrect, D is incorrect, and E is incorrect. Now I understand A and C They read the same, but that's a difference between the second part, which says the reaction is at equilibrium and the reaction is in steady state. And most of you have written it that equilibrium option is incorrect. So we'll see what is the difference between equilibrium and steady state and why both of them are correct. Both of them have the same value and can be the conditions. Why? So, well, let's first solve it. So this is what I was asking, and I see most of you have got the answers correctly. But just in case someone missed out, so we have the values given to us is K1, which is the enzyme plus substrate binding rate constant, which is the first one. Second one says rate constant for dissociation, so that is K minus 1. And then we have the formation of product, which is breakdown of ES complex. So that is K2. Now, we know Kd, which is dissociation constant, is basically here. The equilibrium between enzyme substrate complex and E and S. So Kd is generally K minus 1 by K1. And that you have calculated. While the second one, Km, as we know, it is K minus 1 plus K2 divided by K1. So that comes to 0.05. This one is correct. So based on this, of course, the last point is incorrect because Michaelis-Menten equation constant is 0.04. D is incorrect because again it says dissociation constant is 0.04, which is not correct. And your B is incorrect because it says the dissociation constant is 0.04. So this B, D, E makes sense. Now why is A and C correct? So let's look into first what do you mean by equilibrium conditions? Sorry. The Michaelis constant defined by K M Kf plus K. K on, okay, substitution given value 7. Are you saying you're getting different values? Maybe I have, okay, I'll stop here. What looks different to you here? We are basically doing the same calculation, right? If I'm not wrong, because you are sub adding and then, okay. Okay, Dipali, maybe I'll come back to this in a while. Let me just quickly give you the solution for this complete this question, and then I'll come back and see what we are trying to achieve here. Okay, so here we have equilibrium and steady state. So let us first understand what does these conditions mean and why do both the conditions give you the same answer. So when you say equilibrium condition, it means that the forward and the reverse reaction rates are equal. So the concentration of the reactants and products remain constant over time. And there is no net change in the system. So basically K1 is equal to K minus the reaction in the forward and the reverse direction are equal. While in steady state, which is what enzyme kinetics uses as an assumption, the assumption applies to the concentration of ES complex. So enzyme substrate complex. Now, the assumption here is the enzyme substrate complex is constant over time. So here what happens is the formation of, so here also in forward direction, it is formation of ES complex. In reverse direction, it is breakdown of ES complex. So that way also what we mean is a steady state condition. So if you see in both the condition, your KD still remains the same because it is irrespective of what we are considering it, because KD is about dissociation constant, and the dissociation constant works both in the equilibrium condition as well as in the steady state condition. Did that make sense? Because Kd is basically just the breaking of ES complex, and the ES complex is constant here, but it is the formation of ES complex, the step of formation of ES complex that is taken for consideration Kd when we are looking at equilibrium condition. So in both of the condition, Kd is the same value and it pertains to the same equation or pertains to the same metric that we are looking into. So that's why in the options given here, the dissociation constant is true when the reaction is in equilibrium. At the same time, it is also true even if the equation is in steady state, because both the assumptions Kd remains same. let me know any doubt. You can put in the chat box or unmute yourself and let me know. Right. Coming to Dipali, I'll come back to the chat box. Yes, Dipali, do you have anything to, or I didn't understand what did you try to show? Maybe something is missing in the values here. So maybe you could explain. Because what I see here is Km, I see K of plus K cat and K on. So I'm expecting that is to be divided by K on. And then basically we are substituting the same values. So is there a doubt or are you confirming that your values are the same? Okay. I believe Dipali is either trying to contact us or write somewhere. In the meanwhile, we'll move to the next question so that we move on with the topic and come to the new topic. Right. Again, different unit, like different concept, but based on equations and numerical. So you have a enzyme glumalase, which synthesizes mu galactose by linking one residue of glucose and maltose. Now, what we are considered with is K1. So reactions for this reaction, the K1 is 2 into 10 to the power 5 per mole second. K minus 1 is 3 into 10 to the power 3, and K2 is 8 into 10 to the power 4. K1, K minus 1, K2 is given to you. Then you are given that enzyme catalyzes formation of 146040 mu galactose molecules per minute. You have to calculate specificity constant. So you need to remember what exactly do we calculate, what is the formula for specificity constant. We did specificity constant in the previous session. So you can try to remember that and solve this. It will be a good recap for all the topics that we did in the previous class. E. Okay. I'd like to bring your notice to 2-3 things here. First is look at the units. So your K1 and as in mole per second, your answer is also in mole per second, but your formation of the product is in molecules per minute. So you have to bring all of these into same unit. So be careful of that point here. A. Okay. We'll wait for one more minute if anyone else wants to answer, and then we can discuss. Okay. So, well, so the answer is A, 5861.06 per mole second, per mole per second. And we'll see how. So, well, this is what you are supposed to do. The, first of all, the formula for specificity constant of an enzyme is Kcat by Km. Okay. Now, Kcat is basically how many molecules are is the enzyme catalyzing, that is, or forming. That's there. Now, I told you that the unit is different. Everything in the answers and the question is in seconds except for this one value. So we'll convert this from per minute to per second. So we have done that. We got the value of Kcat in second. Now we will calculate Km from the given K1, K minus 1 and K2. We already know it is K2 minus 1 plus K2 divided by K1. That one we know. That much we will solve and we'll get the value of 0.415. Now simply put it in the formula of specificity constant, which is Kcat by Km. So 2434 divided by 0.415, which gives us 5865.06. Does that make sense? If it's okay, then we'll begin the new topic, which is fresh. We'll discuss freshly in this today's session. Okay. All right. Okay. Let's do it. So, like I said in the previous session, the last part of enzyme is about the inhibition, and we will see what are the different types of inhibition you can have in enzyme kinetics. What are their effects on the enzyme kinetics? How do they look on the LB plot? And how many different types of inhibition are there? So let's first discuss the ones that are given on the side. And let's begin with competitive inhibition. So it's inhibition is basically something that impedes the reactions. So competitive inhibition, as the name suggests, there's a competition. What is the competition between? So your enzyme is always there, your substrate is there. So what is competing? An inhibitor is competing with the substrate for the enzyme, because we are interested in the enzyme kinetics. So what we're trying to look into here is, for that given enzyme, how are the substrate and the inhibitor competing? So in a competitive inhibition, for them to compete, for any inhibitor to compete with substrate, the idea is that they will fit in the same active site. They bind to the same active site. So the inhibitor here has a structural and chemical similarity to the substrate, and it hinders substrate binding by blocking the active site of the enzyme, right? So the inhibitor here competes with the substrate for the active site. As you can say here, the inhibitor and the substrate bind to the same active site, and it can bind to the enzyme and then block this enzyme, and it is rendered unavailable for the substrate to bind to, right? So what happens is it binds and it does not lead. So it, because it is binding to free enzyme, there is no more formation of enzyme substrate complex. Now remember one thing, this inhibition is reversible inhibition, in the sense this inhibitor here, when it binds to the active sites, it's not bound like very tightly. It's not a covalent bound. So it's not covalently bound. So it can be removed. How can you remove this effect when you have this inhibitor which is binding competitively? You increase substrate concentration. So you know that when it is increased substrate concentration, the substrate have better chances of binding at the active site than the inhibitor. So if you increase the substrate concentration here in this kind of inhibition, then you have the chance of overcoming the effect of the inhibitor, right? Now, when you have the inhibitor binding to the enzyme, what is the effect on the enzyme kinetics? The first is your Km increases. So Km, Michaelis-Menten constant, is also a way to interpret the binding affinity of the enzyme and the substrate. What is the affinity of the enzyme to the substrate? So if the Km is, hello, any doubt? No? Okay. Yeah. Sorry. Where was I? Right. So Km is basically the concentration of substrate where the V is equal to half of Vmax or Vmax, right? So basically, if your Km is high, it means it takes a lot of substrate to reach the half of velocity, maximum velocity. It means the enzyme is having lower affinity for the substrate. That's why it needs more of the substrate to reach its Vmax half. But if your affinity is too high, then you need very less amount of substrate to bind and reach the Vmax. So your Km is basically low. If your Km is low, your affinity of the enzyme and the substrate is too high. Right? Now, in this condition where you have inhibitor which competitively binds to the enzyme, here after binding, what happens is your Km increases. Now, since your inhibitor is blocking the active site, you now need more of the substrate to reach the Vmax, right? While the Vmax, however, remains unchanged. Why? Because when you are putting very high substrate concentration, your inhibition is removed. So inhibition removes with your Vmax still remains the same, because you can remove the inhibition and still you have the same amount of substrate binding to the enzyme. So your Vmax, as you can now see in the plot, your Vmax here is a constant. So this line here, let me start show my pointer. This line is the normal line that we see, that we have been seeing so far. This is the uninhibited enzyme kinetics. Now, when you add an inhibitor, what you see is your Vmax remains constant, but your Km, it moves towards the right? Because your Km is increasing. So since your Km is increasing, your this value minus 1 by Km is shifting towards the 0. Okay. So you need to remember. So this plot, there are different types of plot for each of these inhibition. This you need to be very clear about which plot is forward. I have a lot of questions today in the session which will help you clear up these topics so that you don't get confused. So, but for now, what you need to remember is in competitive inhibition, Vmax remains constant, Km increases. That's why in the plot, your minus K, 1 by Km shifts towards the 0, but your Vmax remains the same, right? Okay, that's one. Now let's look at the second kind of inhibition, which is non-competitive inhibition. The name suggests, right? It's not competing with the substrate. There is no competition. It's in contrast to what you have been looking in competitive inhibition. If competitive inhibition, it is basically enzyme and so substrate and inhibitor fighting for the same active site. Non-competitive means it doesn't matter. It binds to some place else. So here the inhibitor, of course, binds reversibly to an allosteric site. Allosteric is site which is not the active site for the substrate, any other site. So binds to an allosteric site, causing a change in the enzyme's overall 3D direct structure, and that's why lowering its catalytic activity. Right? Now, in competitive inhibition, because it is fighting for the same active site, if you increase the substrate concentration, that inhibition effect can be reversed. But here, you can see here, the inhibitor is binding somewhere else, while the substrate is binding somewhere else. So, even if you increase your inhibitor substrate concentration, here you cannot reverse the effects. So you can see the inhibitor can bind to the enzyme, to the free enzyme as well as to the enzyme substrate complex, because it is binding somewhere else on the enzyme. So even if the enzyme has its substrate bound to it, it doesn't matter to the inhibitor, because inhibitor is binding to someplace else on the enzyme. So it can still bind to the enzyme, whether it is free or whether it is bound to ES, right? So what happens here is on the kinetics, Vmax, as you see here also, Vmax is decreasing, as you can see here. When it is binding to the enzyme, its structure is changing and it can no longer give or form the product, because it is catalytic activity is lowering down. So your Vmax is basically decreasing, as you can see here, right? So your uninhibited is here. This line is uninhibited. Your for the inhibited, your Vmax here goes here. This point of 1 minus 1 by Vmax shifts upper, right? While your Km remains unchanged because Km is basically the affinity of your enzyme to the substrate, and here inhibitor doesn't care about the active site of the enzyme for the substrate. It is binding to someplace else. So the active site is still available for the substrate to come and bind, but it can bind, but it will not give rise to the product. And that's why your Km value remains constant. So that's why minus Km 1 by Km point, that is the x-intercept remains constant while your y-intercept changes, which is what? Which is Vmax decreasing. Your Vmax is decreasing. So this point here goes up because it's 1 by Vmax, right? Right. Now, so this was, first one was competitive. This is non-competitive. So you remember this in this way. Competitive is easier to understand. Non-competitive is exactly opposite of it. It doesn't bind to the same place. Now we have uncompetitive, which is the third type. Now in uncompetitive, the inhibitor binds only to the enzyme substrate complex. So here it is no more binding to the free enzyme. It needs the formation of ES where it will bind. So it needs this formation to, or this complex to form, where it will then bind, and then it will impede the activity of the enzyme. So your product doesn't get released yet, right? So what happens on the kinetics? See here, in the kinetics, your Vmax is decreasing because the enzyme is now trapped in ES complex, which is why your total number of active enzymes goes down. This is what is happening with the previous inhibition also. Here, however, your Km is also decreasing because you no more have any this ES is if once the ES is forming, you don't have any free enzyme left. So since this enzyme inhibitor complex is stabilizing the substrate binding, you have now less substrate is needed to be made because it favors the formation of ES. So you have faster forming of ES. That's why your Km also decreases, right? So your Km decreases. So you can see here, Km moves here. So Km decreases. So minus by 1 by Km moves away from 0. And because it is not breaking down further into E plus B, your ES is also stuck. So that's why your Vmax is also decreasing. So both the values are decreasing, Km and Vmax. So it becomes a parallel line to the uninhibited line. Okay. Right. So let me summarize this here in this slide. So you have competitive, you have non-competitive, and you have uncompetitive. This slide is what summarizes the entire stuff in basically in tabular form. So for competitive, the binding site is active site of the enzyme for the substrate. So that's why there is competition. When this inhibition happens, your Km increases while your Vmax remains unchanged. And you can overcome that by substrate, increasing the substrate concentration. Non-competitive, exactly opposite of competitive. So it binds to an allosteric site, so it has no effect on the Km, while the Vmax decreases because the enzyme substrate complex no more breaks down into enzyme and product. Similarly, for uncompetitive, which binds only to ES complex, you have a decrease in Vmax as well as decrease in Km because it favors the formation of ES complex, right? So this all was reversible where you can still have this non-covalent bond formation, while there is something called irreversible binding of inhibitor, which is basically the inhibitor binds and permanently disables the enzyme's activity. That is due to the formation of covalent bond between the inhibitor and the enzyme. And that's an irreversible inhibition, right? Okay. So is this clear? Okay, we'll do several exercises that will get clear one by one. So let's begin with this simplest one. So this is easy. The action of which class of enzyme inhibitors can be reversed by an excess of substrate? This is simple. This is very easy. This is what we have been discussing so far. So competitive inhibitors, because if there is competition, only then if you increase substrate, due to Brownian motion, substrate will bind to enzyme more effectively. Okay, let's do this. So you have this graph here, which is an activity for an enzyme pepsin, which is in the presence of inhibitors P and Q, right? So if it is inhibited by P, it is in this dotted line. If it is inhibited by Q, it is in its dashed lines. Look at the nature of the lines and tell me what nature of inhibition is by P and what is the nature of inhibition by Q. Be competitive and non-competitive. Okay. Aditi, can you take that? Yeah, maybe 1 minute if you want to give the answer. B. Cool. As you people have got it correct. So as you can see in P, your Vmax is constant, which is competitive. In your Q, your Km is constant, which is non-competitive. So that was correct. Right. Next. No, so given below are 4 plots obtained from separate experiments on inhibition kinetics. The velocity is V and the concentration S and the concentration of inhibitor are plotted. So you have different units, V by V, V plotted against V by Vs, 1 by V, 1 by S, 1 by V, 1 by S. So now looking at this plot here, which one do you think refers to competitive inhibition, or which ones do you think refer to competitive inhibition? Think of what is competitive inhibition. You should be able to get it at the very instant. What do you see in competitive inhibition and which ones of the graph show here that value? Okay. C is apparent, yes. But do you think any other also show the same trend? And let me tell you, there are 2 answers to this. So C, you go, people have got right. There is one more. Can you guess that? Remember, competitive inhibition has your Vmax constant. That means your y-intercept will be constant. Exactly. Y-intercept will be constant. If you remember the nature of the plots, one plot had parallel lines. One plot had always x-axis as constant. One plot had always y-axis as constant. A and C, basically A and C. And you people got it right. Exactly. In both this, you see the V is constant, and that is with the nature of a competitive inhibitions plot. So you got that right. Well done. Okay. Now, in an in vitro dehydrogenation reaction of succinate catalyzed by succinate dehydrogenase, malonate is added. Which one of the following curves represent the effect of malonate on the catalysis of succinate dehydrogenase? You need to, this is a very specific example of an inhibition. You give it an attempt, and then I will tell you which specific example this is of in case you get it incorrect. So succinate dehydrogenase and malonate. This is an example of canonical example of the enzyme inhibition that we study. And which one do you think refers to the graph for that kind of inhibition? Okay, A. Anjali says A. Do you want to take a guess, Aditi? So, for the looks of it, the first one is competitive. The second one is here. This is non-competitive. Third one here is uncompetitive. So, if you know this example, okay, let me give you the answer. It is an example, it is a canonical example of the competitive inhibition. So if you know that, we know that Vmax is constant. So this is the graph for that. So you need to know this is a very canonical example for that inhibition. Okay, let's do some numericals quickly. Okay. So coming back to the enzyme kinetics to end the topic. So you have K1, K minus 1, K2, and ET. Calculate Vmax. Very easy question. Just to wrap the topic up once again. You are supposed to find out Bmax. In which formula do you have Bmax and ET? And what is the rate constant used there? You just need to use that value and the answer is straightforward. B, okay. Okay, anyone else? Okay, let's discuss the answer and then we can check if you are correct. So like you said, it's P, that's correct. I told you we are using Bmax. We have ET, we just need to know Kcat. And we know that in a one-step catalyzing reaction, K2 is equal to Kcat. So we have the K2 value with us, we have the ET value with us, we simply multiply them and the answer is 3 into 10 to the power minus 2. Okay, next. And this is second last question. So second last question for the enzyme kinetics. So now there are 5 sentences here. I'll leave it to you first to read and then tell me which are the correct options, and then I will discuss one by one each of them. A, B, D. Okay. 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 So the correct statements are A and B, which you got correct. Just a second. Yeah. So you said A and B are correct, which is correct. So for a competitive inhibitor, when the enzyme is saturated with the substrate, the S and the S to I ratio is 7. is to 2, Vmax remains unchanged. We have seen that already. That's correct. So when K2 is rate limiting, Km is equal to Kd, which is also correct. This is what it means here. K2 so this is the Michaelis-Menten constant that we know of. So when K2, this thing is way less than K minus 1, you can simply substitute this as Km being K minus 1 by K1. And this we know is dissociation constant. So when this is rate limiting, which is very, 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 very slow, so your Km is equal to Kd, right? Now the third one, which is K1, K2, K minus 1 being these values, your Km refer to the enzyme's affinity. Kd refers to enzyme affinity for sure, right? Because Kd is dissociation constant. The greater the dissociation constant, the lesser the affinity, because it means it's breaking down faster, right? But that Km being equal to Kd is only under this condition when your Kcat is 2 or when your K2 is very, very less. But if you see here, your K2 is not negligible or not very less. So you have to consider this. And when you do that, your Km becomes different from your Kd. And then your Km doesn't really show the affinity. It gives an idea, but it is not the perfect correlation for your enzyme's affinity. So that's why it is incorrect here. Yeah, and you people got that right, so it's correct. So uncompetitive impedes the terminally by terminally binding ES complex. So before I give the answer for this, uh, someone said it's correct. What did you mean by terminal here? Because the answer is in the terminal word. So I'm guessing that you wrote it is correct because it is binding terminally. So what did you understand by the term terminally here? Or in other words, why did you think this is correct? Okay, no problem. Okay, sure. So remember in uncompetitive inhibition, the inhibitor is binding to the ES complex. So it's a forming an enzyme substrate inhibitor binding to ES complex. Exactly. I thought that. So terminally here does not mean it binds to the end or it terminates the reaction. No. Terminally means it is irreversible binding. That word terminal is basically to entirely combat it. And I told you in irreversible binding, you have entirely stopping or permanently disabling the function. So that's the correct meaning. And that's why when you think in those lines, your D is incorrect because it is not in irreversible binding. Uncompetitive is still reversible binding. Okay. Next, uncompetitive inhibitors cause an increase in Km as the substrate required to reach a certain level of Vmax increases. And we know that this is not the case because in this, Km and Vmax both decrease. And you people got that correct. So, yeah. So the terminal point made sense. Terminally basically binding irreversibly. So if you bind irreversibly, there is no chance for you to come back to your original. All right, the last question on enzyme kinetics, and then we move to carbohydrates. Again, I'll let you read first. Let you give me the answers for the incorrect statements, and then we'll discuss each point step one by one. So I think there is one word that we haven't discussed, suicide inhibitors, but when I come to that, I'll tell you what that refers to. The other we have more or less discussed in this session, previous session. So it's basically all the points taken together in a question, and whichever is incorrect, whichever you think is incorrect. A, B, C, and E. Okay. All right. Shall we? Okay, I'll wait for the answers there. Okay, someone's typing. A, B, C, and G. A, B, C, and G. Okay. Okay. So let me give F and G. So A, B, C, F, and G. Okay. Okay. So I think I've got the answers. First, let me give you the answers. So A, B, C, F. Those are the incorrect statements, right? I think A, B, C, most of you got correct, or all of you got correct for that matter. And we'll look into the later four. So the first one says specific activity of the enzyme increases with an enzyme in Km, which is not correct. Specific activity is basically, as we know, it measures enzyme efficiency. And Km is basically representing, which we have also again discussed, it is the substrate concentration where the enzyme reaches half of Vmax. So higher the Km, if there is an increase in Km, it means there is low substrate affinity, which means it requires more substrate to reach optimal activity. So if that's the case, then your specific activity, which is also a measure of the efficiency of the enzyme, is also decreasing because your Km is, remember I told you when your Km is increasing, it means you need more substrate to reach your Vmax. That means your specific activity is also decreasing. It's not increasing, right? Okay, next, competitive inhibition causes a decrease in Km by binding to the active site of the enzyme. No, it increases because it binds to the active site. So it has to now compete for greater substrate. Like it requires greater substrate concentration to reach its Vmax, half of Vmax. So next, Km, which is the affinity of an enzyme for a substrate, is lower upon the addition of non-competitive inhibitor. That's correct. We have discussed it so far. That is incorrect. Sorry. We have discussed it how it is not the case, because in non-competitive, Km is constant. The Vmax is changing. Next is general acid-base catalysis. Side chains of amino acid in the enzyme act as acceptor donor the proton. This we did in the previous session, which is correct. Now, I think E, most of you have not got it right, which says the energy released upon the increase in entropy aids enzymatic catalysis. So, did you people say that was incorrect? I think, yeah, you did say it was incorrect. So, well, this is correct because here it says the energy which is released upon the increase in entropy, which is what is the increase in entropy. So when you're binding, when there is binding of substrates to the enzyme, there is binding, so there is reduction in entropy. But the overall enzymatic catalysis releases from the release of water molecule, and that release of bound water, that release is what leads to increase in entropy. And we know that in aqueous environment, in water, your enzymatic activity is enhanced, your reaction is enhanced because it has the reorganization, it gives the soluble aqueous environment for the in reaction to take place. So there is decrease in the activity when the enzyme substrate come together, so your chaos reduces, but then there is release of water as well, which increases the entropy, and that gives us the water aqueous environment where the enzymatic reaction takes place, and that's why it favors the enzymatic catalysis, right? So that's why this is correct. So this is not here. Next, for suicide inhibitors, there's a decrease in Km alone, and the last one says for suicide inhibitors, there's a decrease in Km and Vmax. So F is incorrect. That means G is correct. G means G is Km and Vmax getting both decreased. So first of all, let us first understand what are suicide inhibitors. Suicide inhibitors are the inhibitors that we haven't discussed. It's basically those inhibitors that bind irreversibly to the enzyme and then permanently inactivate it. So because it permanently inactivates the enzyme, it decreases Km and decreases Vmax both. Okay. So suicide inhibitors are the inhibitors that fall under the category of irreversible inhibitors. And they decrease both Km and both Vmax. Right? Any doubt in this section of enzymes? Otherwise, we move on. Yes, yes. Please type in your questions or you can unmute yourself and ask.
Ma'am, we have been told in previous class that enzyme do not affect the thermodynamics, because we know that the enzyme won't be affecting the equilibrium. So, like equilibrium is one of the thermodynamic property, it will also not affect other thermodynamic properties. So we put it as incorrect, because entropy is also a thermodynamic property of the enzyme.
Yeah, but the question here is not about enzyme taking part in the entropy, right? The question, the increase in entropy, if you see the energy which is released upon increase in entropy, the increase in entropy is coming from the release of bound water molecules, which you remember, if you remember in the catalysis, in the water-based catalysis, there is release of water molecules that enhances the entropy, and that water molecule there is used for the enzymatic catalysis. It is one of the how do you say, one of the mode of catalysis. We have acid based catalysis, we have water based catalysis. So this point referred to the aqueous environment, which is because of the release of bound water. We are not talking here about in terms of enzyme, how enzyme binding to substrate is changing the entropy. That entropy, as you have already said, it doesn't affect thermodynamics. There is a change in entropy, but that does not really affect the thermodynamics. But what actually enhances is an release in the bound water molecules. Is that clear? If not, let me know, then I can try to explain it better.
Actually, ma'am, this is the same question being explained by Sir. So his explanation was this, like thermodynamics related to this. But your explanation is entirely different from him, because you involved water molecules and correlated it with the entropy and enzyme catalysis. So I got little bit confused, like which one is correct.
So did he say it was correct? Did he say this statement is correct, or did he say this statement is wrong?
He said this statement is incorrect because thermodynamic property won't be affected by the enzyme.
So I believe that when he was talking about energy in general, it is the overall, when you just look into the enzyme substrate as the complex. So where I was talking in perspective of the water molecule mediated enzyme catalysis. Well, Well, when you talk
Okay.
in that sense, it is incorrect, yes. But when I talk, I was talking about a very specific condition where we have aqueous environment and release of water-bound molecules. So, but
Okay, ma'am.
okay, I understand the doubt here. So, it's safer to go with the general assumption when it is just we are discussing about enzyme and substrate. So, maybe we'll put it as incorrect. So, for others also, what she just pointed out was that as we know that enzyme doesn't participate in thermodynamic differences, so it doesn't bring in change in thermodynamics. So we entropy is a part of thermodynamics. So when you just broadly consider enzyme and substrate and the general catalysis, there you might not see a role of entropy in that overall reaction, because you're just looking at enzyme and substrate in a general way. But what I explain, when you look in that perspective, this statement is incorrect because it talks about thermodynamic differences, and that doesn't happen in normal enzyme-based catalysis. But I was referring to was the when you have an enzyme catalysis reaction, which is mediated by in a step by the release of bound water. When you have that release, which increases the entropy, and we know that there is water-based catalysis. In that sense, you do have an aid in the enzymatic catalysis. So unless it is specified clearly in the question, just go with the general assumption, and then in that sense, it is incorrect. I hope it makes sense now. Anjali, was that clear? Yeah, I hope.
Yes, ma'am.
Yeah, because I was talking about specific example, but yeah, if you see in general, maybe the safer way to go is take a general assumption and uh, let it be incorrect. Yeah, correct. Makes sense. Thank you for that. Okay. So let's move to the next part, which we've already done in the first session. But let's just quickly look into this week's session. So if you have already looked into week four's lecture notes, in carbohydrates, they've shown you monosaccharide, polysaccharide, disaccharides, and then they have given you some properties of monosaccharides, and then they have given you several examples of carbohydrates. So what I have done is I have first explained the properties, which we have already done in the first session, uh, but we'll do it once again. And all the examples are there in the questions. So we'll use the questions as a platform to discuss all the different examples. Yeah, cool. So this is not, because this is a repetition, it shouldn't be very new to discuss. So well, carbohydrates I've already seen. The name itself tells you what all does it contains. It contains carbon, it contains oxygen, and it consists of hydrogen. So CH2O, N. That's a formula for monosaccharides. That's a general formula for monosaccharides. Monosaccharides are basically, we have also done this. We know they are of aldose and ketose group. If they have an aldehyde group, that's an aldose sugar. If they are consisting of keto group, it's a ketose sugar, right? So you have fructose and you have glucose. These are the prime example of monosaccharide, which you see here. Disaccharide are basically two of these monomeric unit coming together. That is the maltose, for example. Polysaccharide is basically when you have multiple units coming together in linear and in branched form. This we know already, we have seen. This also we have extensively discussed in the first session. If you haven't, the lecture videos are uploaded where we have discussed what are enantiomers. So basically, enantiomers are non-superimposable mirror images of one another. What are these mirror images of? So, and why are these mirror images? These mirror images are because of the stereochemistry. So you will have chemicals which have same sequence of atoms, same bonds, but their 3D shape is different. Their positioning or their stereo chemistry is different. Now, if you put those two chemicals or put those two compounds on top of each other, they do not superimpose. And we have already looked into the first class. Yes. So in first class, we saw that, however, hands are non-superimposable, even though they have the same 4 fingers and 1 thumb. But if you put them on top of each other, you don't exactly have a superimposing nature. And that's why these two are called, and these two are called enantiomers. So these is an example of understanding what is enantiomer. So you have two non-superimposable mirror images. That much we have seen. And we also saw how here, this you can see here. So the enantiomers are named D and L. We saw this also. And we knew how to name D and L also. What we saw was that when we have to write D, our group, our OH group has to be on the right here. And when we have to write L, it has to be on the opposite. But what do we mean by D and L? With D, we mean dextro-rotary, and with L, we mean levo-rotary, right? Now, what does that mean? So these enantiomers, they rotate plane polarized light in a positive direction. So when the enantiomer rotates in a clockwise, how does the clockwise moves? Like this, right? This is clockwise movement. So how do you remember D or L, which one is clockwise and which one is anti-clockwise? You just need to remember, in clockwise, how do we move? So in clockwise, we move like this. So this is similar to forming D. So this is dextrorotary. So the opposite is counterclockwise movement, which is levorotary. Similarly, this is what I told you in D also. When you are writing D, you are moving towards the right. So if your functional group is on the right, it is D. If your functional group is on the left, it is L. So this is how we have done naming conventions of D and L. Some similar convention is for R and S, which is there in the first session. You can go and see how did we do first session. Yeah, where we looked into how do we name R and using R and S and conventions, right? This topic again we had done in the first class. Yeah, first. So where we are looking into epimers. So epimers are basically a pair of stereoisomers, right? So these stereoisomers, again, like I said, they have same constitution and molecular formula, but their orientations differ. And they are basically differing. Let's say there are many stereo centers. So the position where they are, these two structures are different. They are, that is called the stereogenic center. And one molecule can have several stereogenic center. That's because, let's see, D glucose and D mannose first. Okay, CHO, CHO. This also is correct. This also is correct. Only the first and the second here. Okay, OH on the right, OH on the right, and CH2OH. However, when you look at the second carbon, you have OH on the right and H on the left. So then they are similar. They're identical for all the places except for one site. That site is where they are different from each other. That site is where they become a stereoisomer, and that position you can take and you can call them as C2 epimers. The sorry, yes, yeah. So if you say D mannose and D glucose, you look into C2, they are epimers. If you look into D glucose and D galactose, the same glucose is same at the second site with galactose. However, it is different at the fourth carbon, where it has OH on the right, while this has H on the right. So this is a C4 epimer. And this is what is referred to as in the third point. So a single molecule can have several stereocenters, which is what leads to it having several stereoisomers. Okay. The same molecule D-glucose is a C2 epimer with D mannose, while it is a C4 epimer with D-galactose. Epimers are basically the site where they are different from each other. That one side. Right. So that's there. This is something they understood. Now, if you remember, or maybe I can go back here. So these are all linear structures, right? D-glucose, L-glucose. This representation is in a linear form. But we also represent our glucose or our sugar in this cyclic form. And for this, if you remember, we had done projections. We'll do that again next slide. But how do you make this straight chain structure here into this cyclic structure here? That cyclic formation is called hemiacetal or hemiketal formation. So how do this happen? So molecules which have aldehyde or ketone, which is basically they have an alcohol and a carbonyl group in the same molecule. So here you have alcohol and you have a keto group. So if you have that, sorry, if you have this both groups here, then they can undergo this formation of hemiacetal or hemiketal, which is cyclic in nature. And this intramolecular reorganization is favored because it is more stable rather than them forming this structure with some other molecule. So what exactly happens? So this is the same molecule. This is one of its carbon and this is one of its group. This group has ROH and this carbon has a carbonyl. So this is carbon has an oxygen group attached to it. So there is an attack from this OH to this C, and then there is a reorganization of the electrons, and then ultimately it leads to the formation of hemiacetal, right? Because here we started with an aldehyde group here, CH. So let's look into this exactly what it's for. So this, remember, if we have done Fisher and Hayward projection. So this is how you move from a Fisher projection to a Hayward projection. We'll do it a bit slowly so that every point is registered easily. So let's look at all these 6 carbons, which is in glucose. 1, 2, 3, 4, 5, 6. So in the 5th carbon, you have this OH. So this carbon gets bound to the first carbon. The first carbon has CHO group. The second carbon has an alcohol group attached to it. So this we saw already, this bond forming. Now when it is forming, of course you can imagine a straight structure where these two parts are connecting to each other, they automatically form a cycle or a closed structure. And this is what is going to happen here. So if you now look into this, you have this C, which is the fifth carbon, fourth, third, second, and the first one. So this rearrangement takes place here. This C, this O comes and binds to the C. There is O here. So ultimately what happens here is you have this O left. So the C binds to the O. This H is remaining here. This O here has got connect. This H has moved to this O. So you ultimately have an OH here, H here, O here, and the CH2 group attached to the fifth carbon. Okay. Now, what are these? Where do these go in the ring when you are putting them across? So whatever is on the left side goes up in the ring. Whenever you are putting a ring, wherever you are putting, this goes up. So here for these carbons, let's look into this. Let's start with the second carbon. Second one has H. This H should move up in the ring. So H has gone up, OH has come down. Third carbon, OH on the left goes up, H goes down. Fourth, H on the left, H goes up, OH comes down. Fifth, however, because of the rearrangement, CH to OH goes up, H comes down. And then when you go to first one, this OH comes up and H goes down. But this OH could have formed in the other direction also. So based on this OH group, we have beta and alpha anomer. Okay. Yes, it is complicated, but that's what the whole idea here is. We'll take it step by step. So you have a cyclic formation. You have all these, where to put these? These goes on the ones on the left go on the upper hand or the upside of the inner ring. But on the C, where this rearrangement is taking place, the OH can form here or the OH can form here, obviously, because there's a rearrangement taking place here. But when both the alcohols face the same direction, it's a beta anomer. And we will see when this OH goes down, it is the alpha anomer. So alpha, beta, D we know because the D was here, dextrorotatory, and glucopyranose because that's the name of this component. So here, this is what exactly we saw right now, OH and OH being on the same side. While if that OH had formed below, it would have been an alpha. So alpha and beta. So alpha, beta, DL. Are these clear? Yes, I am on the screen. You can unmute or you can type as well.
Ma'am, like the small d and small l we can interpret by looking at the molecule, because it is like we can rotate the plane polarized light in either of the direction. By looking at the molecule, we can't decipher whether it is a small d or l.
Yes. Well, that's why that information. So this dextrorotatory and levorotatory information is already always given with the molecule. We know that we have done this question, right? Most of the natural amino acids are in D. So we know, so those information are given with the molecule. But as you mentioned, that's an information with the molecule that we get. We can't look into the structure and tell that it is D or L, small d or small l. Yes.
And ma'am, we can represent small d with plus sign as well.
Yes.
And
That's what.
there are two terms like configuration and conformation. I never understand the difference between the two and how to put d, l, small d, capital D in either of them, like whether it is the conformational changes or the configurational change.
Um, yeah, I understood your question. Okay, I will get back to you in a while when I give you the first question to solve, because I don't want to confuse you further. So I got the question, conformation and configuration. That is the question, right?
Yes, ma'am.
Yeah. So when we are solving the first question in this set, I will look into this and I will get back to you. Till then, just be with me. I will get back to you with the answer.
Okay, ma'am. Okay.
Yeah, sure. Right. So, yeah. So this is hemiacetal formation. Similarly, you have hemiketal formation. So the carbon which forms the cyclic form is not a acidic aldehyde group but an ketone group, and this takes place in furanose or fructose basically. Okay, the same nomenclature here applies. If the OH group is on the bottom side, it is alpha. If this OH would have been on the upper side facing this CH2OH, it will be beta. Right, and this alpha and the beta, these are the anomers. So we have seen epimers, we know anomers, we know enantiomers, and we will also see what is called mutarotation. Mutarotation is basically the opening and the closing. So this is open form, this is closed form. So the opening and the closing, this repeats continuously in an ongoing interconversion between anomeric form. So if you have alpha D-glucopyranose, it can open up to form D-glucose. It can again close to form beta or open up to form D. So this interconversion takes place. And when you look at their specific rotation, they have their own values of specific rotation. So for example, alpha D glucopyranose have plus 112, plus being positive direction. So they rotate tripline polarized light in the plus direction. So plus 52.7, plus 18.7. But what happens when you put them at equilibrium, or when you keep the solution, you will see that most of them are in beta form. Some of them, 36% is in alpha, while you have very less of this open aldehyde form. And the observed rotation of this solution is plus 52.7. This means that these are in equilibrium. They're always interchanging their conversion from one form to other. And this closing and opening repeating is called mutarotation. And this is another property of the forming of the anomers, between the anomers, because there are two types of anomers that can form. So you have these what do you say, cyclic formation of alpha and beta in a solution. Okay, right. So mutarotation, anomer, hemiacetal, hemiketal, epimers, enantiomers. These are all the topics that you will see in your slide. So I've tried to cover them here as much as possible. So the next one is disaccharide. In simple terms, they are basically two sugar coming together. They are formed by glycosidic linkages. The glycosidic bonds can be of two types if they are N-linked and they are O-linked. So in N-linked oligosaccharide, you have the sugar bound to a nitrogen atom. Where will you find nitrogen? Let's say asparagine in a polypeptide chain. So in the asparagine, if it binds via the nitrogen, it is called N-linked, simple to understand. While O-linked is again very simple to understand. It's basically bound to the O of the serine and threonine. So if two sugar units come together, there's glycosidic linkage. But here, when you have a sugar binding to a polypeptide chain, they can have two type of linkages. They can have an N-oligosaccharide or they can have an O-linked oligosaccharide. This is also there in your lecture notes, so this shouldn't be very confusing. Lastly, we have also looked into this. We have polysaccharides. So we have this long chain of carbohydrate molecules. They can be linear, they can be branched, they can have alpha 1,4 linkages, they can have alpha 1,6 linkages. And we have seen this in, you have cellulose, glycogen, and starch. So cellulose you generally find in plant. So there you have beta glucose as the monomeric unit, and they are bound to each other by 1,4 linkages, but there is no branch structure. In starch, which you find again in plant, there are two forms. You have one polysaccharide which is called amylose, which is unbranched structure, but then you have amylopectin, which is a branch structure. So when you have unbranched structure, you have alpha glucose, which is bound in alpha 1,4 linkages. But when you have amylopectin, the linear form is alpha 1,4 linkages, the branched is alpha 1,6. And then in animal, you have glycogen, which is again alpha glucose, which is again branched. So you can see if it is branched in animal, it is called glycogen. If it is plant, it is amylopectin. Anything? Any doubts? Well, mute to ask. Yes, and remember the units. So no branching units of alpha glucose is amylose, while beta glucose is cellulose. So this difference you need to remember, right? Okay. Right. So, like I said, I'll give you the questions, and from the question, we'll discuss the several examples and the different molecules. So, which of the following statements regarding saccharides are false? Serum antibodies about alpha D glucose and different component. First, you give an attempt, and then we can discuss. In the meanwhile, do let me look up into your question about configuration and conformation. B. Okay. ACB. Uh, okay, let me give the answers. Someone, so you people have said B is false or AC false. So the question was about false statements. So the first one is serum antibodies are glycoproteins where the carbohydrate moiety, the one that is repeating, is an alpha D glucose and alpha D galactose, alpha D mannose. Well, first of all, it is serum antibodies, which is glycoprotein, is correct, but the repeating unit is not these. It's rather N-linked and O-linked oligosaccharides, antibodies, as we know of it, right? And then we have the N-linked glycans, which and O-linked glycans. So those are the repeating units. This are not the repeating unit is incorrect, right? While the second one, which you got right, alpha D glucose and alpha D glucose disaccharide serves as the circulatory sugar in insect. Do you know the name of this compound by any chance? What is this compound called? Alpha D glucose bound by trehalose, exact. Trehalose, right, correct. So trehalose is the circulatory sugar in insects. Next, you have the sulfated glycosaminoglycan hyaluronate is the key component. So you will see here why it is incorrect. So there is sulfated, there is glycosaminoglycan and hyaluronate, and this is said this is the component of synovial fluid. Hyaluronate is the component of synovial fluid, but that is not sulfated. What actually is sulfated is the glycosaminoglycans, which are heparin sulfate, chondroitin sulfate, and keratin sulfate. So this glycosaminoglycan is sulfated, but not the hyaluronate. So that's why when the statement is incorrect. And lastly, chitins, as we all know, they are the polymer of acetyl glucosamines, which are connected by beta 1 for linkages, right? Right. So you can try these questions and then we can discuss the answers. A, D, B, and D. No, sorry. A, B, D, D. Can you also give me the question numbers? I can understand D and B and D. Okay. D and B. Okay. D and B. Everyone on the same page. D, B. Question 2B. Question 1A. Okay. D and B, and most of you got it right. So the first question is, in carbohydrates, the hydrogen and oxygen molecule is present in the ratio CH2O, repeating n times. So CH2O. So H2 2 times, H2 times O1. So 2 is to 1. And which n carbon is anomeric in alpha fructose? Here. So we know that this carbon, as we have already looked into the fructose structure, this OH can go up, it becomes beta, this OH can go down, it becomes alpha. So the C2 is the anomeric carbon. And that is also something that you people got correct. Good. This also will be very easy for you people to do. Okay. Let me look at the answer first. DB 1B. Okay. AB, AB, DB. Okay. AB, right? Uh, yeah. Let me first see if you have any doubt. Okay. So the transporting sugar in insects found in the hemocoel in the wall of fungus pore is tree hallose. There's nothing to explain here, but that's just that you should know that in insects you have tree hallose, while the other glucose, sucrose, and lactose you find them in different other components. For example, glucose, you probably know it's the energy, it's fundamental energy source, while sucrose is a major component of plant, and lactose is rather found in milk. So that's why when you say transporting sugar, it's tree hallose, right? And then the nitrogen containing structural polysaccharide, by name itself you should know that's chitin, but by there is another way of you can use information that you can use. So you see this is chitin and this is pectin, cellulose, and hemicellulose. What does the question say? The question says the nitrogen containing structural polysaccharide is found in the cell walls of fungi and arthropods. So that means the structure should have a nitrogen. In chitin, you have nitrogen here. Here. So you do have chitin with nitrogen. But look at pectin, look at cellulose, and look at hemicellulose. They have no nitrogen in their structure. So that also gives you that this is not the correct answer for it. But we also, of course, it's a well-known fact that fungi and arthropods have their exoskeleton made of chitin. Right. Okay. Next one. one AD CABA. Oh, I have a mix of answers here. Okay, CACDBA. All right. CA. Did that option come? CAAC. Okay, mix and match. Okay. So the first one is when an aldehyde group of an aldose reacts with one secondary, it is what structure? So we know that then this reaction takes place, it forms a cyclic structure. And when it is taking place with an aldehyde group, this is hemiacetal. This is not an acetal group. Acetal group doesn't have that cyclic form. That's a different chemical reaction. The reaction that we saw is an hemiacetal with a cyclic structure. So that was C, not a acetal, because that was the whole discussion, right? Hemiacetal. And the second one is when you have anomeric form, they are alpha and beta anomers. Right? We also did this. We did this exercise today. So yeah. Okay. Next, I think this is the last. So these are again the only monosaccharide that lacks. This is, so you have four monosaccharide. Which one is asymmetrical center, and the repeating unit of cellulose is called what? C CD. Okay. CD. Okay. B. Okay. Glucose, which is basically glucose. Okay. So B and C. Let me see how many of you got it. Wait, D, D. Okay. You said sucrose. Okay. So I think the confusion is because it's just not no. So the repeating unit of cellulose is called a cellobiose units. Okay. While let's look at the first one. So let the first one says which one of these are optically inactive. What is asymmetrical center? Basically chiral center. Chiral center means that it has all four groups different, right? That was will mean, right? It lacks an asymmetrical center. It basically doesn't have any asymmetrical center. Okay, so let's look into first glyceraldehyde. Look into glyceraldehyde. It has one CHO group, one H group, one OH group, and one CH2OH group. So this is a chiral center, right? Let's look into fructose. I think some of you also wrote fructose. So fructose, so let's look at this carbon. It has this entire group here, CH2OH, H and OH. That is a chiral center. Let's look at this one. This has this different group here, this different group, and then H and OH, chiral center. So likewise, you can see it has multiple chiral centers. Let's look at glucose. You of course know glucose has multiple chiral centers. Fructose also has, this also has. But let's look at dihydroxyacetone. CH2OH, CH2OH on both sides. This is not an asymmetric. This is symmetry because it has two similar groups on the either side. So this is not asymmetrical center. So that's why it is dihydroxyacetone. So what you need to remember is the structure of the component and then look into if it has asymmetrical chiral carbon. If it has chiral carbon, it is optically active. Okay. Right. If that made sense, then let me know. Then I will try to answer the doubt on conformation and configuration. Okay. So Anjali, yeah, Anjali. So you asked about confirmation and configuration. Can you first explain that what you know already so that I don't get too much into the details? So what do you think about confirmation and configuration, and what does the doubt exactly? Anjali?
Ma'am, it
Yes.
mainly talks about the arrangement of atom in a molecule, but I don't know like what is actual, why it is different, like configuration we say or conformation. Basically, both are the arrangement of atom only.
It's, yeah, arrangement, yes, but when you were reading, I'm pretty sure you would have come up across one very important difference between these two. Can you remember that? It had something to do with interconversion or
Yes,
something to
ma'am.
do with,
In one case, the for the interconversion there is bond breakage something, but others it is not.
yes. So when, so in confirmation is basically, how do I say it? So you have a bond which you can change and it can give you another form. So your confirmation is basically different. You're talking about arrangement, yes. You're talking about different arrangement when we're talking about interconversion right now. So in confirmation, if I change a single bond on the component itself, it becomes a different arrangement. Okay, so let's say this is a compound, this is a 3D structure, and I move it like this one bond I move, and this becomes a different conformation. I haven't broken the component yet, but in configuration I cannot do this. I need to break this bond. I need to break this bond to give you two different configuration. These two forms that I'm talking about, let's say about configuration, it is not possible if I just rotate a bond, if I just move one bond here and there. I need to break the components apart from each other. Then I will have two configuration. Configuration is basically the arrangement in their native form. If I move them in their native form and it changes the it changes the arrangement, it's conformational differences. It's just conforming to the arrangement of the bonds that I want to make. I have a bond, I just change the place, it becomes a conformational difference. Configure is basically the makeup. In very layman terms, configuration is the build-up, the way it is made. So if you want to change the configuration, you have to break apart the bonds so that it becomes two different forms. So conformations are flexible. You can have different conformation in the same component, though it is not separable. It doesn't have, they are not inseparable, but configurations are separable because you are breaking the bonds and trying to form two different arrangement. Did that make sense, or it's still a bit confusing?
Yes, ma'am. In case of we say whether it is alpha or beta, so we are
Hmm.
not breaking the bond.
Hmm.
It will be come under confirmation.
You tell me, what do you think?
For me, it's not bond is not breaking there, so it should come under confirmation.
So you're saying I can make alpha and I can make beta by just changing this in the same molecule by changing the bond? Or do I have to think about this? Do I have to break my alpha, or do I have to break then bond to form a beta? So that you remember that slide we looked into for the muta rotation. If that is possible in the same bond, then it is confirmation. If that is not possible, it is configuration. Anyone else who wants to answer this? That's why I said, remember the muta rotation slide. Do you think it's a configuration or conformational change? There was something in the configuration muta rotation slide as well, that can give you the cue whether it's configuration or conformation. Okay, based on the discussion we had, what was muta rotation?
Ma'am, the
Then
interconversion of the two forms, the alpha and
correct.
the beta.
So here, right? And what did I say? This form, for this form to be form this, for this structure to form this structure, what should it undergo? Opening and closing. So what is happening? It is disrupting and then it is forming a different structure. In this alpha D-glucopyranose, this OH will not move upon itself. For it to go up itself, it has to form the cycle again. And if it is forming the cycle again, it means it is first breaking down, forming a linear structure, and then it is forming a cycle wherein the OH can go upwards. So that will become beta. So now what do you think? It's configuration or conformation?
Yes, ma'am, it is configuration.
Yes, exactly. So wherever you
One more.
have, yes, yes.
Ma'am, like what causes this muta rotation? Like we say that glucose will be interconverted into its either of the two form. But what causes this muta rotation? I don't
This is
understand.
all equilibrium driven, right? So the attacks that you see here, the formation that you see here is because of these groups here, and these groups keep the electron pairs keep rotating. So these are all interchangeable. Wait a minute, I'll open this again. So when it is this structure, these OH, which still carries the electron, can still these bonds can break again because of the equilibrium. The equilibrium pushes it to form a linear structure, but when it is a linear structure, it will again go back to this structure where it can form the hemiacetal. So it's basically driven by the equilibrium of going and forming a straight line structure. Did that make sense? No.
Like, ma'am, either of the form is not stable. So the equilibrium. I don't understand why to attain the equilibrium. Uh,
So you're asking why does muta rotation occur? That's what you were asking, right?
yes, ma'am.
Like why do you see even this change from one to another?
Yes, ma'am. Like what? Why? Like we say that it is changing. Either it wants to become in the stable conformation or the stable state. Maybe that's the reason of the interconversion. But I can't correlate here why there is a need of interconversion in either of the two forms.
So so see the difference between them is not just in the structure, it's also in the difference of their plane polarizability, right? How much do they rotate? How much do they rotate the light? So that factor also is in effect when there is a solution. How much of light is coming? How much can they rotate? How much is the equilibrium forcing them going back to? So it's all about. So that if you know about you know deuterion, right?
Yes, ma'am.
Yeah, it doesn't need to lose its plus charge or negative charge. It has both the charges on itself, but it still does the going and coming back from the plus state to the original state. That's driven by the equilibrium at that onset, at what values it starts with. Like at yes, Dipali, you want to say something to it? Do you want to type? No, she has left, I think. Yes, sorry. Where was I? I'm so sorry. I left. So we were saying why is muta rotation occurring, and that I would like to believe is because of the differences in the plane polarizability that is occurring here. The equilibrium and the bending of light is what is favoring their conversion from one to other. But I understand the difference here. Maybe I'll try to put it in a better way in the next class. Would you give me that much time?
Yes, ma'am. Like in the real life, I can't correlate why muta rotation is occurring. Like we can put the glucose in the room temperature, we won't see any of these things. Like the real life example of the muta rotation, like you said now, the deuterion, we do know that deuterion occurs at a particular pH or the pi. There is correlation why they
Yes,
get deprotonate or protonate or this
correct,
deuterion form, we can correlate, but we I
correct.
can't able to correlate with the muta rotation in the real life. So
Tell me, when does muta rotation happen Is it when the glucose is also in solution, then is glucose in dissolved in solution? That is
Yes,
when the
ma'am.
deuteration, right? So that can
Yes.
occur in the solution. The same way your pH is affecting the deuterion, the same way glucose in the solution depends on, because it's a polar structure, because it is optically active. Whenever it comes into a plane polarized light, it will have a it will rotate. It will rotate the light to a certain extent. So that's why it muta rotates. So, and to do that, it has to form the cyclic structure, which is very much possible because it has those two groups which can readily attack each other in the solution.
Okay, ma'am. Okay. Okay.
Yeah, because it is in the solution, and it affects the light. It has a plane polar. It's optically active. So whenever it is in solution, it tries to bend the light. And how does it does that? Because when it is in its structure, it has those two groups which can attack each other and form a cyclic structure, which then has their specific optical activity at a certain rotation. Yeah.
Ma'am, yes, ma'am. One more question. What if we are putting that glucose in the water, like making a solution, but not in the light condition, in the darker condition? So this phenomena won't happen just because there is no light, so there will be no rotation as such.
uh could say that. You could say that, but how do you ensure no light? What do you mean by no light? How do
No
you
light,
stop?
like we are intentionally keeping it in the dark condition. Like we, there are conditions.
Then the whole idea of plane polarized light goes away, right? And then it, of course, takes away the entire thing. That you cannot measure it in those points. See, the attack of it being, the chance of the groups being attacked will still be there because it's in solution. That inherent property is still there, but it rotating, it can form a cyclic structure, but we have no reasons. We will have, there will be no push from the equilibrium to go into a certain form because there will be no light where it favors a certain kind of structure. So that cyclic structure can still form. It will. It's not that it will not form because the cyclic structure formation, it can still be possible. It is only, it's how do I say? It's enhanced when there is a light because it has to polarize the light, so it will try to form a cyclic structure. I hope it's circular, but I hope I made some sense.
Okay, ma'am. Thank you. You actually made sense now. It's clear.
Yeah.
Yes,
Okay.
ma'am. Thank you.
Yeah. Okay. So yeah. So today's I finish here only, but yeah, I have so I did mention that I will do lipids in the next session. But today I think it's already very late for me to ask. But if you have any topic specifically that you want to revise or do it, it's not clear, please put them in the chat box in the next session. I will put that in the first few time only, so that I work on those and we try to work on things that which is not clear. Okay. You can put it whenever you feel like. We can work on that so that it's easier for you to grasp the subject, whichever topic, whichever week we have covered already, so we can do that better. Yeah. So if no more doubt in today's session, then we meet at each other in the next session. Thank you. Thank you so much. Thank you.